Good morning, students, and hello, everyone. So now we will be covering a second section of physics lectures for revision of class 11 topics, wherein we will be looking at Newton's laws of motion and friction as the next chapter, the next section of our syllabus. So let us begin. Okay, so we will look at basically the free body diagram method for solving Newton's second law. We are all aware of the Newton's laws of motion. The first law being the law of inertia, okay, that simply states the property of inertia of a body, wherein it wants to continue in its state of rest or uniform motion until and unless it is acted upon by an external force. The second law, which basically tells us the definition of net force acting on a body. The net force acting on a body equals to the rate of change of momentum. This is the proper statement of Newton's second law. Now, since we know that the linear momentum of a body is mass into velocity, so if the mass of the body is constant, which is in fact the case with a rigid body, then rate of change of linear momentum becomes mass into rate of change of velocity, which becomes mass into acceleration. So we also have the working formula of Newton's second law, which is applicable when we are talking about a constant mass, where the mass is fixed or constant. Whereas we should also understand at this stage that if in case the mass is variable, we are talking about a variable mass system. Okay. Like for example, a rocket system, or let's say a melting block of ice, okay, or a tank from which liquid is leaking out or whatever. So if the mass is variable, then m and v are both instantaneous quantities. So in such a situation, what we have to do is we have to understand that the net force, which is rate of change of momentum, will become equal to rate of change of mass into velocity, which will further become rate of change of mass with respect to time into instantaneous velocity plus instantaneous mass into rate of change of velocity. So of course, we will look at the application of this more in a different chapter where we look at systems which have variable mass. But one should remember that it's not a universal fact that net force is equal to mass into acceleration. It is a conditional fact when the mass of the body in concern is constant. Otherwise, the universal condition is that the net force acting on a body equals to the rate of change of momentum. That is in fact the statement of Newton's second law. Okay, so that's about first two laws. And as we know, the third law is the action reaction principle. That every action has an equal and opposite reaction. So if a body A applies some kind of a force on body B, then B applies equal and opposite force on A. Okay. So this is the principle of action and reaction. So in this section, we will mostly be looking at the application of Newton's second law by the vector analysis through free body diagrams. Okay. So the next important thing for us becomes the free body diagram. So if we have a certain object which is under the action of multiple forces, etc., then the free body diagram consists of a diagram where the body's mass is represented by a point mass, and all the forces are shown to be emanating from the point mass or originating as vectors from the point mass. Okay, so for example, these forces here will be shown like this. Okay, and then we will develop some kind of system of axes. If required, two-dimensional; if required, then three-dimensional, whatever be the case. And the forces are resolved. So forces are shown as vector arrows in the free body diagram. Originating from the point mass. Then next, resolve the forces into components. Okay. And finally, solve this equation in component form. Okay. So that is summation of x component of forces is mass into x component of acceleration, and summation of y component of forces becomes mass into y component of acceleration. So this is basically the application of Newton's second law in component form according to the system of axes which is chosen from the free body diagram. So obviously, to implement this third step, we will have to resolve the forces. Okay, so let's look at some examples to understand this. So for example, we have a situation like this. On a smooth frictionless surface, we are applying two forces on this body. So suppose it's given to us that the magnitude of F1 is equal to 50 newtons. The magnitude of F2 is equal to 30 newtons. And alpha and beta are both an angle of 37 degrees each. Okay, so let us understand the free body diagram. Okay, for this block. And let's calculate find its acceleration, because it's on a smooth surface, and the normal reaction acting on it. Okay. So you can just take a minute and try out this. We will discuss this. I'll put up the free body diagram and you can compare your solution with mine. Okay, so let's figure this out. So what we will do here is we will first of all represent the forces as vector arrows which are emanating or which are originating from the point mass. So the two external forces which I have shown over there will be like this. These two arrows will be F1, which is of magnitude 50 newtons, and F2, which is of magnitude 30 newtons, such that with respect to my horizontal axis and vertical axis, which I will take as my X and Y axis over here. So we'll take the horizontal direction as our X axis and the vertical direction as our Y axis. So now you can see that with respect to this axis, this one is at an angle alpha here of 37 degrees, and this is at an angle beta, which is also 37 degrees. Okay. Now, apart from this, what is happening? There is the other forces which are, there are the other forces rather, which are the gravitational force that the earth is pulling down the body with. Okay. And there's a normal contact force which the ground is applying on it. So you know that whenever a body is in contact with a surface, there is a what we call a normal contact force, which is the contact force acting perpendicular to the plane of contact, okay, such that it prevents motion along that plane or it balances the other force normal to that plane, so that the net force in the normal direction should become zero. And under the action of all this point mass, which was 10 kgs, should have an acceleration in this direction. Its acceleration will be in the horizontal direction of A. Okay. So what we roughly understand, as forces acting on it, there is this F1, there is this F2 that we were applying. This angle was alpha, this angle was beta, whatever. But mg and the ground is applying a normal contact force. And under the action of all this, it's accelerating like this. So this is now converted into a proper free body diagram like this. This is the free body diagram. Okay. Next, what we want to do is we want to resolve the forces. Okay. So we will resolve these two forces to begin with, F1 and F2. So F1's component along the x-axis and F1's component along the y-axis. This will become F1 cos alpha, and this one will become F1 sin alpha. So F1 is resolved. Okay. And similarly, we will resolve F2. Okay. So we can remove F1 from the analysis now. Similarly, we will resolve F2 into components. Okay. Okay, so this is F2 sin beta, and this is F2 cos beta. So we have resolved out F2 also. Okay. So now we can see that along our x-axis, okay, the component of net force should be equal to mass into x component of acceleration. So the net force along the x-axis we can see is F1 cos alpha plus F2 sin beta, and this should be equal to ma. Okay. So this becomes our first equation, and solving it, we will get 50 into cos 37, which is 4 by 5, plus 30 into sin 37, which is 3 by 5, will be equal to mass, which is 10 kg into acceleration. Okay, so we have acceleration, which will come out to be 5.8 meters per second square. So that gives us this. Now next we need to calculate the normal reaction. So for that we will look at the forces along the y-axis. Look at the resolution of forces along the y-axis. Now we can see that the y component of acceleration is 0 because the body is moving along the x-axis. So because of that, the forces will get balanced. Okay. So normal reaction will balance, normal reaction plus F1 sin alpha minus mg minus F2 cos beta should be equal to 0. So this is our second equation. So from this we will get the value of the normal reaction. So normal reaction you can see will become mg plus F2 cos beta minus F1 sin alpha, which we can now see. Mg will be 100 newtons. This will be 30 into cos 37, so that's 4 by 5. Minus, this will be 50 into sin 37. So the normal reaction will become this much. So the normal reaction is becoming 94 newtons, whereas the acceleration was this much. So this is an example of the application of the free body diagram method to implement or apply Newton's second law and find out various things like let's look at another example. So we have a 30-degree smooth inclined plane. And in this inclined plane, we have placed a block like this of mass m. Okay. And on this, we are applying some external force, but we are applying the external force horizontally. So the mass of the block is, let us say, 20 kilograms. Acceleration due to gravity we will take as 10 meters per second square. Now, an external force F is applied horizontally so that the block remains at rest in equilibrium. So equilibrium means net force is zero. Okay. So we have to find the magnitude of this external force. Okay. So the method we will use to implement this to find the magnitude of the external force will again be the free body diagram method. Okay. So I would like you to just give this a try once. Try by making the free body diagram. Make the blocks free body diagram and do the vector analysis on it. For net force to be equal to zero, equilibrium condition. Okay, so just give this a minute, try this out. We will discuss. Okay, so let us look at the free body diagram of this one. So the forces acting on it will be the external force that we are applying horizontally. Okay. Obviously, the weight of the body which acts vertically downwards. Okay. And that will be, in this case, 200 newtons, because the mass of the body was 20 kilograms. Okay. And now the other thing which is there, which will become very significant, is the direction of the normal reaction. So for that, we have to understand this very carefully, that the inclined plane is, let us say, along this axis. Okay. So this inclined plane this is at an angle of theta with respect to the horizontal. So the direction in which the normal contact force acts will be like this. It will be perpendicular to this inclined plane. It will act along this axis. Okay. So that is why here this angle is 30 degrees. So this angle will be 30 degrees. Okay. Whereas if we draw another line which is normal to this axis, that line will look like this. Okay. So this is the axis which is perpendicular to the inclined plane. Okay. So this is the inclined plane's axis. Okay. And this is the normal to the inclined plane. So the normal contact force will now act along this line. This is the idea. Okay. And also you can see that here this angle is 60, therefore this angle will become 30 degrees. Okay. And what we want is that the net force should be 0. So the acceleration should be 0. So now the condition for the acceleration of the block to be 0, or what we call the equilibrium condition, okay, is that net force should be a null vector, or the vector sum of F, mg and normal reaction should be 0. So there are a couple of ways we can implement this now. Let's look at that. So the easiest way to implement this will be what we call the Lami's theorem, okay, or the equivalent of the sine rule. So it's equilibrium of three forces. Okay. So for that we can always use the sine rule of a triangle, or what we call Lami's theorem. Okay. That is the easiest way to deal with something like this. So I will just quickly illustrate that. So these are the three forces whose vector sum has to be 0. So we had understood that okay, these angles are like this. So this angle here becomes 120 degrees, and this angle over here becomes 150 degrees. Okay. So we have the general form of Lami's theorem that if the vector sum of A, B, and C is equal to 0, and these angles are alpha, beta, and gamma, then the condition for this is that A upon sine alpha will be equal in magnitude to B upon sine beta will be equal to C upon sine gamma. So we'll apply that over here. So we will get N upon sine 90 degrees, okay, will be equal to F upon sine 150 degrees will be equal to mg upon sine 120 degrees. Okay, because that's how these forces are working out. So you can see that this angle is 90 degrees, this angle is 120 degrees, and this angle is 150 degrees. So n upon sine of the opposite angle is equal to f upon sine of the opposite angle is equal to mg upon sine of the opposite angle. So now we have to just implement this. So n by 1 should be equal to f by half should be equal to mg, which was 200 newtons divided by root 3 by 2. So as you can see, n will be equal to 400 by root 3 in magnitude, and f will be equal to 200 by root 3 newtons in magnitude. So these become the solutions for this. So this is the what I would say is the best method of solving this particular problem, because you're just solving for equilibrium of three forces. So you don't need to get into resolution and all that. You can use this very easily. The alternative is, of course, you can resolve forces and work it out. Okay. So you can also work out a resolution of forces method. So if you want to use component algebra, you can always do that. We've seen that this angle is 30 degrees. So you can see that this angle will be 30 degrees. Okay. So if we resolve normal reaction into components, this will become n cos 30. And this will become n sin 30. Okay. So now net force is 0. So along the x-axis, summation fx should be 0. So f should be equal to n sin 30, or f should be equal to n by 2. And along the y-axis, so we should have f cos 30 should be equal to mg. So f root 3 by 2 should be equal to 200. And now solving these equations, you will see you'll get F as 400 by root 3 newtons, and you will get the normal reaction as 200 by root 3 newtons, which is the same result we had got earlier. So without any fuss, you can get it by component method also. But as I told you that the sorry, bit of a correction here. The solving will give us that the normal reaction from the second equation is 400 by root 3 from equation 2 that you can see over here, and substitute that in the first equation. So F is equal to n by 2. So F will become 200 by root 3 in newtons. From this equation, we're getting this here. Okay. Okay, so these are a couple of basic examples. Now let us pick up something which involves, pulleys and tension in a thread, etc. So let's look at a situation like this. Okay, so this is a smooth fixed pulley. Okay. And this is a light and inextensible thread. And these are both smooth surfaces. And this is also obviously in a vertical plane. So given that mass of A is, let us say, 60 kilograms. Okay. And mass of B is 40 kilograms. So we have to find the accelerations of the two blocks and the tension in the thread. Okay, so just take a look at this question before we populate it with all the forces, etc. So obviously what we'll be doing here is we'll be applying the free body diagram method to understand the accelerations of the two blocks. Okay. And now one thing I might want to point out here is that because the masses of the two blocks are different, okay, and the heavier block is on the side which is having lesser inclination, it's a bit tricky in the beginning to understand which direction the acceleration will happen in. It's a little bit tricky to analyze whether the block B will be sliding down its incline and A will be sliding up the incline, or vice versa, that A will be sliding down the incline and B will be sliding up the incline. So there is a method to understand that, but we can also do one thing, that we can just make an assumption about any direction and solve our equations according to the assumption. If the acceleration on solving comes out to be a negative value, that means the direction of acceleration just has to be reversed. So either way, it's okay. We can analyze from the force components and actually find out before we solve our equations that what is the correct direction of acceleration. Or on the other hand, we can just resort to assuming some direction of acceleration and solving our free body diagrams with that assumption in mind. And if we get the value of acceleration with a positive sign, then our assumption is okay. Whereas if we get it with a negative sign, that means the direction of acceleration is reverse of our assumption. So these are two different approaches we can take to solving this particular type of situation. So I will discuss about them. Okay. So let's begin by understanding here a basic sort of analysis of what all forces are acting. Let's first try to understand that before we get into, solving the whole thing and making the free body diagrams. Okay. So in this type of situation, we will keep one analysis very straightforwardly in mind, that whenever we have an inclined surface at an angle theta, then the weight of an object can directly be resolved into components like this. Okay. And this angle is always theta. So when we resolve it into components, the component of weight which is normal becomes the cos component, provided we are talking about the angle with the horizontal for the inclined plane. And the component which is parallel to the inclined plane, that becomes mg sine theta, becomes the sine component. Okay. So this thing we will implement from the beginning. Okay. So here, if we see, this component, okay, will become sine component. And remember, mass of A was given to us as 60 kg. So this will become 36g. Okay. Whereas this component will be cos 37. So that will become 48g. Apart from that, there will be tension acting on this. Okay. And apart from that, there will be normal contact force. Be acting like this. Now, similarly, if we look at B's weight now, B's mass was 40 kg. Okay. So the component of its weight down the inclined plane or parallel to the inclined plane, the sine component. So 40 into sine 53, okay, will give us 32g. Okay. And the component of its weight normal to the inclined plane, so 40 into cos 53 will be 24g. So this will be 24g. Okay. And again, there will be some normal reaction acting, which will be this. Okay. So if we resolve the forces this way, then it's very clear to us from the beginning what is the direction of acceleration. You can see that this component of weight, the sine component of A's weight, which is 36g, is trying to pull the system in this direction. Whereas this one's component of weight, which is 52g, that is B's weight sine 53 components, is trying to pull in the opposite direction. Okay. So which one is dominating? So we can see that because A's weight's tangential component is greater than B's weight's tangential component. Therefore, the direction of slipping will be such that A slides down the incline and B slides up the incline. So now I know my direction of acceleration will be like this. Okay. And once I know that, next I can just write the free body diagram equations. Okay. So for A's free body diagram, so we just saw that for the block A, we had this component of weight, (36g), this component of weight, (48g). We had tension, we had normal reaction, and the acceleration was in this direction. So we'll take this as our x-axis, this as our y-axis. So we have along the x-axis, we have the equation 36g minus t is equal to 60a, because remember the mass of A was 60 kg. So that's our equation 1. And along our y-axis, of course, we have the normal reaction balancing 48g. This equation is complete on its own. We don't need to do anything. Now, similarly, when you look at B's free body diagram, so there we had seen the forces this was 32g and this was 24g. Tension, there was normal reaction, and B had to accelerate up the inclined plane like this. So you take this as your x-axis, this as your y-axis. So here along the x-axis, we have the equation T minus 32g is equal to 40a. That's our second equation. Because remember, mass of B was 40 kg. Okay. And of course, along the y-axis, we have the equation normal reaction balances 24g. So that is a complete equation in itself. We don't need it. Okay. Now we can solve equation 1 and 2. So 36g minus t is equal to 60a. That's our equation 1. And t minus 32g is equal to 40a. That's our equation 2. Now we can just solve them by adding these. So 36 minus 32 is equal to 60 plus 40 e. So our acceleration becomes 4 by 100 g, or it becomes 2g by 50, or in this case it becomes, if we take g as 10 meters per second square, it becomes 2 by 5, or 0.4 meters per second square. So this becomes the complete working of this. Okay. Now over time you will get more practiced with this kind of thing. So what will happen is, once you get practiced with this type of question, you will not need to write so much actually. You will look at this free body diagram and immediately you will understand that if you take this whole thing as a system, okay, then you can see that the acceleration of the system will become this force minus this force divided by the sum of inertia of this block 60 kg plus inertia of this block. You will come to this conclusion directly. Come to this conclusion directly. But yeah, if you are less practiced with this kind of thing, then you first need to learn how to write these equations properly after making the free body diagrams and solving. Correct. Now, next situation we will look at is something which has a system of pulleys and constraint relation. So constraint relations will become important throughout mechanics for us in several different situations. And we will learn several different methods to work out the constraint relations. So here to begin with, we will see the simplest method, which is basically what you can say is the thread length conservation method. So suppose we have this kind of a situation now. We have a smooth surface like a horizontal tabletop with a pulley attached right at the end. And the thread is going around another pulley. Okay, so our system consists of something like this. So we have two blocks like this and two pulleys like this. So this is a smooth surface. Excuse me. This is a vertical situation. So P1 and P2 are smooth and massless pulleys, or they're very light pulleys. Okay. This is a massless and inextensible thread. And masses of block A and B are given to us. Suppose mass of block A happens to be, let's say, 10 kilograms, and mass of block B happens to be 5 kilograms. Now we want to find the acceleration of block A and acceleration of block B and the tension in the thread. Okay, so these are some of the things we want to find out here. So first of all, we'll have to understand that there is a relationship between the magnitude of A's acceleration and the magnitude of B's acceleration. So in this situation, if A has an acceleration like this and B has a vertical acceleration like this, we have to first of all develop the relationship between A's acceleration and B's acceleration. So let's understand how we'll develop that relationship. So for the constraint relation, okay, that is, you can say this ratio, we'll use a principle over here. We'll use the constraint that the thread is inextensible. So that means its length is conserved. So that means that to begin with, this was our situation initially. So that thread length is suppose L. Now what is happening after some time, suppose the block B together with the pulley has got pulled down. Okay, so you can see that this system has got pulled down by delta Y. So during that time, it will pull the block A by some delta X. So this thread length at this new time compared to the original time, this thread length has increased on this side by 2 times delta YB, but on this side it has decreased by delta XA. So this has to be equal to the original thread length, which means that A's horizontal displacement is twice of B's vertical displacement, which means that the rate of change of A's X coordinate must be twice in magnitude to the rate of change of B's Y coordinate. Okay. Which means that at any instant, if A has a velocity VA, B has a velocity VB, the magnitude of A's velocity is twice the magnitude of B's velocity, which also means that differentiate this one more time and the acceleration of A is 2 times the acceleration of B. So this is the constraint relation that we are looking for. This is the constraint. Because the thread length remains fixed, so they have to move in such a way that their accelerations are in 2:1 ratio. This is the meaning of the term constraint relation, and this is how we implement it over here. So the method we are using for implementation of this constraint relation, in this particular case, it is the thread length conservation method. So we are using the method of conservation of thread length. Now this is not the most convenient method to use. There are shorter and shorter and sweeter methods of developing this constraint relation, and as we move along we'll learn about them. But fundamentally this is one of the core methods. Okay, and there's a method that will always work in all situations involving system of pulleys and threads. Okay, so this becomes the first equation that we have. Now the rest of the things is about free body diagram. So if we look at the forces in this diagram, we can quickly make the free body diagram from that. Okay, so if we just analyze the forces that are acting on the different blocks, now that we know the ratio of their accelerations, there is tension acting like this. Okay. There is some kind of a normal reaction that is acting on A. Okay. And obviously there are the weights of the two blocks. Okay. So if you look at A's free body diagram, okay, we have a single tension and its weight. So the important thing for us is that the acceleration of A will come from that tension. Okay. So I think we've taken the mass of A to be 10 kgs. So that becomes our second equation. If we look at our block B, there is a net of 2T acting upwards. You can include the pulley in its free body diagram because the pulley is massless and its own weight is 50 newtons. It has an acceleration of EB downwards. So for B, we'll have the equation weight minus 2T is equal to mass into acceleration. So this equation now will become (50 minus 2T is equal to 5 EB). So this is our third equation. And remember, our first equation was the constraint relation. Constraint relation was acceleration of A is twice of acceleration of B. So we have to solve this system of equations. So what we'll do is we'll substitute this here first. So this equation will become T is equal to 10 into 2 times acceleration of B, or 20 AB. Then we'll substitute this here. So this equation will become 50 minus 2 into 20 AB is equal to 5 AB. So from this, we can see that acceleration of B will become 50 upon 40 plus 5, or 50 by 45, or 10 by 9 meters per second square. So acceleration of A will become double of acceleration of B. So that will become 20 by 9 meters per second square. And you can put that back in this equation to get the tension. So this becomes a typical example of something involving constraint relation and system of pulleys, albeit we have taken a very simple system of pulleys here, just 2 pulleys and a string going around the second one like this. So we have a very simple relationship between the accelerations, which is a ratio of 2:1. As we move along, we'll see more complicated versions of this also. So just make sure you analyze this once, and we'll take it forward from here. Okay, so this is a revision of the concept of constraint relation. Now let's move on to something else, which is a very interesting part of Newton's laws of motion, and that is the concept of pseudo force. So I know a lot of people have difficulty with understanding pseudo force, let alone implementing it. So I will begin with a brief explanation of the concept of pseudo force and inertial and non-inertial frames. So first of all, we should be very clear about the definition of the two types of reference frames. Okay, so reference frames that we are using for the analysis of our free body diagrams can be divided into these two categories: inertial frames and non-inertial frames. So a frame that is at rest is like an absolute inertial frame, and any frame that is moving in non-accelerated motion or in uniform motion with respect to our absolute frame is an inertial frame. But in that sense, it would be very difficult to describe an inertial frame or define an inertial frame, because motion is always relative. So what do we mean by something which is at absolute rest? For example, if you're talking about the earth, then the earth is in various types of motion. It's in rotational motion about its own axis. It's in elliptical orbital motion around the sun. Then the solar system itself is in motion with respect to the galaxy, and Milky Way galaxy is in motion with respect to other galaxies, etc. So this chain goes to an infinity here, and there's no way to resolve it and exactly define what an absolute frame at rest would be. But since all our experimentation as human beings is on the surface of the earth with respect to the ground, so for uh, any physics experimentation that is happening on the Earth's surface, we can describe the ground frame as the absolute frame, or a frame which is at rest with respect to the Earth's surface, that is the ground frame, as the absolute inertial frame. Okay, so we will not bother about the fact that the Earth itself is in accelerated motion with respect to the sun or with respect to the solar system and blah blah blah. What we'll think about is that our experimentation, our human experience is typically on the surface of the earth. So for us, the absolute frame is the ground frame. So our working definition of inertial frame therefore becomes that it is any reference frame which is either at rest or in uniform motion, that is unaccelerated motion, with respect to the ground frame, that is the frame on the surface of the earth, the reference frame attached to the surface of the earth, that is becomes a inertial frame with respect to our experimentation on the earth's surface. Okay, with respect to our human experience, that becomes the inertial frame. Whereas a non-inertial frame, which we will in short form call NIF from now, whereas inertial frame we can call it IF. Okay, this is any reference frame which is accelerated with respect to the ground. Any reference frame moving in accelerated motion okay, with respect to the ground frame. That becomes a simple definition of the non-inertial frame. Okay. Now the next thing is that a body in a non-inertial frame always experiences a type of additional force because of its own inertia as well as because of the acceleration of the frame, and that is what we call the pseudo force. Okay, the term pseudo means imaginary, but we call it pseudo force because the agent of the force is not an external agent, it's an imaginary agent. The force is very real. Okay, so any particle or object or body or whatever in a non-inertial frame will experience a pseudo force, okay, such that pseudo force as you know it is given by a simple relation that it is minus of mass of the body into the acceleration of the frame. So let's call that A naught. Okay. So where m is the mass of the body, particle, whatever. Okay. And A naught is the acceleration of the non-inertial frame with respect to the ground frame. Okay. So how do we get this relation? It's very simple, really. That if you look at Newton's second law in the ground frame or inertial frame, for a body of fixed mass, we have the net force acting on the body is equal to mass into acceleration. Okay. Where E is the acceleration of the body with respect to the ground. Okay. Now suppose we have an non-inertial frame that itself is moving with an acceleration A naught with respect to ground frame. Okay. Then the acceleration of that same body with respect to the non-inertial frame or relative to the non-inertial frame. Okay. So acceleration of which body? The body which is having acceleration A in the ground frame. So this relative acceleration will become its ground frame acceleration minus the acceleration of the this thing, reference frame. Okay. This is coming from the concept of relative acceleration. It is the absolute acceleration of the body minus the acceleration of the moving frame. That becomes the relative acceleration. This is the relative acceleration of the body with respect to the non-inertial frame. Okay, so it is a vector difference of these two. Now compare this with equation 1. So compare with equation 1. Okay, so if you multiply mass on both sides, mass into acceleration in this frame is equal to mass into acceleration in ground frame minus m into A naught. So this is equal to the net force plus the pseudo force. So there's the additional pseudo force that it is experiencing, which is giving it the acceleration A prime relative to the non-inertial frame. So it is from comparison of this actually that the formula of pseudo force comes. That pseudo force is minus of mass of the body into acceleration of the frame. And a simple way to remember the effect of pseudo force is that visualize this, that this is a bus, let's say, which is stationary. Okay. And there's a person standing inside the bus, or there's an object sit on the bus. Now, the moment the bus accelerates forward, it's a very common experience that you will experience a pseudo force backwards. The object will experience a pseudo force backwards. It will tend to slide back unless held by friction. Okay. Or take an experience where this is moving at high velocity. Okay. And suddenly it decelerates. So there is what we call hard braking, heavy braking or hard braking. It creates a deceleration. So immediately these things tend to slide forward. There is pseudo force acting on them. So you can see that the direction of pseudo force is always opposite to the direction of the acceleration of the frame. Okay. And from the earlier formula or the earlier analysis of Newton's second law in inertial ground frame versus the relative motion with respect to the non-inertial frame. Okay. So this is Newton's second law in ground frame. Okay. Then we analyze this with respect to the concept of relative motion. So we got Newton's second law in the non-inertial frame, because we are relating it with the acceleration with respect to the non-inertial frame or the relative acceleration. So we get this kind of relationship here. Okay. So with these things in mind, let us understand some examples of this. So our first and most basic example will be, let's consider an Atwood machine, a simple Atwood machine, inside an elevator which is vertically accelerated. Now this elevator itself is accelerated vertically at, let's say, 2 meters per second square. Okay. And mass of A is given to us as, let us say, 8 kilograms, and mass of B is given to us as 2 kilograms. And the acceleration due to gravity is 10 meters per second square. Now there's a person standing inside the elevator. Let's say that person is Amit. So we have to find the accelerations of A and B with respect to Amit, and find the reaction force acting at the hinge of the pulley, at the pulley's hinge. Okay, consider the pulley to be massless or of negligible mass compared to these weights. Okay. So let us understand this question in detail next to fully understand the concept of pseudo force. Okay, so what we will do is we'll make the free body diagrams of the blocks A and B in the elevator's frame. Now the elevator is an accelerated frame, so it will become a non-inertial frame, and that is the frame in which Amit is present. That's Amit's frame. Okay. So what he will analyze is the block A with respect to the non-inertial frame, which is going up with an acceleration of A naught. This is Amit's frame. Okay. The block A will be experiencing forces, tension, and its weight. Okay. And it will also be experiencing a pseudo force. This will be the pseudo force. Okay. And we can see that A was the heavier block, so A will be coming down. So let's say in this frame, its downward acceleration is small a. So A is the acceleration of block A downwards with respect to Amit's frame. Okay. So we have the equation that weight of A plus pseudo force acting on A minus tension should be equal to mass into acceleration. So we have 8 into G plus A naught minus T is equal to 8A and we are taking A naught as 2 meters per second square and G as 10 meters per second square. So we'll have our equation is becoming like this. This is our first equation. So, going back to this, you can see that with respect to this guy, A is a heavier block, so it will be coming down with some acceleration A. This will be going up with some acceleration A in his frame. Okay, because in his frame the pulley is at rest. In his frame, the tension is acting like this. So now let's look at B's free body diagram. Again in Amit's frame. So B is going up with that acceleration A. Is B's upward acceleration with respect to the non-inertial frame of Amit. Okay, so in his frame now, tension and weight are the external forces which are acting, but there is pseudo force of mass of B into A naught this time, and the tension is dominating. So the equation will become T minus, sorry, the weight minus the pseudo force is equal to mass into acceleration in this frame. Okay. And mass of B was 2 kg. So we have T minus 2 into G plus A naught is equal to 2A. So we have T minus 2 into 10 plus 2 is equal to 2A. So we have T minus 24 is equal to 2A. So this becomes our second equation, which we are getting from this one's free body diagram. So we have two unknowns and two variables. I mean, two equations and two variables and two equations. Okay. So solving, we had 96 minus T was 8A, and we have T minus 24 is equal to 2A. So just add the two equations. So we have the acceleration comes out to be 7.6 meters, 7.2 meters per second square. Okay. So therefore, now we can say that in this guy's frame, okay, so what Amit is seeing is that the block A is coming down at 7.2 meters per second square, and the block B is going up at 7.2 meters per second square. But that's with respect to Amit. Okay. And to find the reaction force on the pulley's hinge, this is a free body diagram of the pulley. Okay. It is massless. So here we need not worry about which frame in which, because the pseudo force and weight will not exist because its mass is tending to 0. So the sum of these two tensions is balanced by whatever reaction force is acting at the hinge. So this reaction force will be equal to 2T. Okay. And T we can work out from the earlier equations. Once you got this acceleration, we can see that this is the tension. Okay. So we substitute that here. Pardon, this is 38.4. This is the reaction force at the hinge. Okay, so this is an example of the application of the concept of pseudo force in a non-inertial frame, where slightly more complicated than a single body in a non-inertial frame, because we have an Atwood machine which is inside a vertically accelerated elevator here. Now, once we have found out these accelerations with respect to the elevator's frame, we can also find the accelerations of A and B in the ground frame by just using the relative motion concept. Okay. So we want to find acceleration of A and acceleration of B with respect to ground frame. We'll just use the fact that acceleration of this is equal to the acceleration of A with respect to the elevator plus acceleration of the elevator. So acceleration of the elevator, if we take this as our y-axis, is E naught j cap, that is 2 j cap in meters per second square. And acceleration of E with respect to the elevator is minus a j cap, that is minus 7.2 j cap. So we can see that acceleration of A in the ground frame will become minus of 7.2 plus 2, will be minus of 5.2 j cap in meters per second square. And similarly, if we analyze for the acceleration of B in the ground frame, that will be acceleration of B with respect to the elevator plus the acceleration of the elevator. So acceleration of B with respect to the elevator is in fact plus 7.2 j cap, because it's going up, and this is 2 j cap. So acceleration of B in the ground frame becomes 9.2 j cap meters per second square. So in the ground frame, it looks like B is going up at 9.2 and A is coming down at 5.2. Okay, but in the elevator's frame, it is that they are having same magnitude of upward and downward acceleration. So this is how we can incorporate the concept of pseudo force in a non-inertial frame and proceed this way. Okay. So thanks for attending, and that's it for today's session. And we will continue with more lectures of Newton's laws of motion along with friction in the next installment. So wish you all the best.